Hello, the internet, and welcome to Open Source Directions, hosted by Quansight, the webinar that brings you all of the news about your favorite open source projects. My name is Anthony Skopatz, your host for Open Source Directions. Co-hosting with me today is Carol.
Hi, listeners. I'm Carol Willing. I'm an active member of the Jupyter and Python community, and I am very happy today to have an opportunity to chat about Extensor and xframe with my friend and longtime Jupyter colleague, Sylvain.
Hello world, I'm Sylvain Corlet. I'm the founder of Quanstack, a Paris-based open source software development team focusing on scientific computing. And as an open source developer, I'm very active in the Jupyter ecosystem. I also do volunteer work in the community as a member of the board of directors of NumFocus. I also organize the PyData Paris meetups, and I'm a member of the Jupyter Steering Council.
Well, with a CV as long as your arm, we're going to get to know you a little bit better. So we're going to have our famous tweet of the week section, where each of the panelists here gets to share a tweet that they've been enjoying in this past week. So Sylvain, you're first up.
So last week we had an announcement by Andrzej Sotik, who released the first version of Fortran, a Fortran interpreter. So you heard right. And so now you can actually use Fortran in a Jupyter notebook. So if you want to know more about this, check out the link that has been shared by Brandon. And you can also try it out on Binder.
Excellent, thanks.
Cool. My tweet comes from Rachel Thomas, who's Math Rachel on Twitter, and her tweet is, the top item on my wish list for AI researchers. Write a blog post to accompany your paper. This is a chance to reach a broader audience in a more accessible format. And I completely agree, not just for AI, but for many scientific things. And she's got some great links as well, which Brandon will share.
Hear, hear. So this last week, Shiraj tweeted, I'm seeing a lot of skepticism from physicists around my Learn Physics in 2 months curriculum. Machine learning enables people to make scientific discoveries without needing as much domain knowledge. See my lecture at CERN last year for an example. To which Stefan Hoyer, a member of the PyData community for a long time, replied, if only it were this easy. Every time I thought this was true, domain scientists have proved me wrong. Machine learning is no shortcut for domain knowledge. Stefan, I couldn't agree with you more. Yeah. So with that, we're going to dive in and learn a little bit more about xtensor and xframe. So very shortly, or very briefly, the xtensor is effectively a NumPy for C++, and xframe is Panda's equivalent slash xarray for C++ as well. So these projects have about 1,300 stars on GitHub and get about 140,000 downloads from anaconda.org. And with that, we'll just ask you a few questions, Sylvain, and have a good discussion here. So, Carol, take it away.
Thanks, Anthony, for the intro. And Sylvain, why was the project started, and what needs does it fill?
So originally, we started the project to support other developments that the Quanstack team was for clients and other projects. So it actually fills a gap in the C++ stack. So mostly the C++ standard library does not provide an ND array data structure or even less data frame. And these are really standard, basic data structures for data science that everybody wants to use. There are some libraries offering some n-dimensional capabilities out there, but that they did not generally offer the sort of flexibility we wanted in terms of having a runtime number of dimensions, being able to operate in data structures from other languages, or even the lazy evaluation that we wanted to have from the start. So also very often the C++ libraries that are written for ND array features, they don't really have a idiomatic C++ feel, and we really wanted to stick to the STL idioms here. Also, Extensor is not just a C++ library, it's also a collection of packages that work well. So it's not really just one package, but more of an ecosystem. So there are two underlying packages. One is XTL, which is a utility metaprogramming package that we use across the stack. Another one is xsimd, which enables high-level wrappers for SIMD intrinsics, meaning single instruction multiple data, and XIMD is the library that powers the SIMD acceleration of Extensor. We have Extensor itself, which is the core ND array library. So too long didn't read, it's NumPy for C++ with NumPy style broadcasting, universal functions. Then we have a number of bindings like extensor blast for NumPy linalg, or extensor IO for reading all kinds of file formats, extensor FFTW for fast Fourier transform, and language bindings, extensor Julia, Python, and R. And so there are also some other interesting packages to bind with Arrow or the Rant ecosystem. And finally, and the latest comer in the stack is xframe, which is essentially a data frame for C++. And to my knowledge, is pretty much the first one to be available. And so xframe is very much to extensor what xarray or pandas are to NumPy in Python.
Excellent. Yeah, I mean, it's quite the ecosystem, as you said. So are there alternative ecosystems or projects out there that you know of?
So there was a project at Continuum a few years back called Dyned, which was, I think, developed very much with Python in mind as a sort of other backend or other library providing NumPy style abilities. But it was a pure C++ library. There is also Boost multi-array, which only supports static dimensionality. There is no language bindings to my knowledge. Eigen has a lot in common actually with Extensor and how it's architectured. Although Eigen is mostly 1D and 2D, and the new Eigen tensor structure only has static dimensionality, no language binding. So it's not really NumPy.
Right.
There is a new project that I can't say too much about from Quansight, which is XND. It's a C library implementing NumPy style broadcasting and features. And obviously, we have all of the tensor libraries from other languages in Python, Julia, and R.
Cool. Sylvan, what technologies are these rich libraries built upon?
So I should probably just start with the C++ programming language itself, because we make use of techniques that were introduced in C++ rather recently, such as verillic templates and advanced metaprogramming. And this was really made possible thanks to the amazing strides that the C++ community has made in the past decade. SIMD acceleration is powered by the xSIMD project that I mentioned earlier. And xSIMD allows operating on batches of size 2, 4, 8, depending on the available chips, and on multiple platforms such as x86 or ARM. And we also include the accelerated implementation of all the basic math functions like sine, cosine, exponential, but that are computed in batches of 4 or 8. The language bindings, they are based on the typical libraries to do bindings for Julia, R, and Python. So PyBind 11 for Python, RCPP for R, and CXXWrap for Julia. And also a lot of the demos that I'm going to do today rely on the clean C++ interpreter that came from CERN. And finally, Conda, the package manager, is a big part of the story. We rely heavily on it to distribute the software. So another library that I really want to mention, it's not built upon it, but I should say that NumPy is like the strongest inspiration for Extensor, and it's actually even in the first line of the description of the package for people who want to know what Extensor is. And essentially, too long didn't read, Extensor is NumPy for C++. And in terms of every single aspect and how broadcasting and how the API has been designed, we are following NumPy very closely.
Yeah, NumPy is the de facto API for all this stuff.
Yeah.
It's just in a kind of a fascinating way, actually. So who started all of these extensor projects and everything?
So Extensor itself was studied by Johan Mabior and myself when Quansight was founded about 2 years ago. But very quickly, like a few months later, we had Wolf Folprecht contributing to the stack. And he's now a core developer of the project with as many commits as both of us. And he works full-time on the project. No, xframe is very much early stage compared to extensor, and it's mostly been developed by Johan Maville and Martin Renou, who is also a contributor to extensor.
Excellent. Who maintains these projects today?
So at the moment, the package is mostly maintained by Quansight, so the company that we work at, our company. But we have some, also, I would say that we have a growing number of external contributions. Beyond Wolf, Johan, and myself, we actually have a new committer, which is Tom Degus, who recently joined the core team. We also had like some core contributions, like important contributions from Airbnb, CERN, folks at INRIA, the University of Heidelberg, and the Netherlands eScience Center.
Wow. Yeah, quite the list. So where do, you've sort of answered this in the previous question, but where do the users and contributors come from? What are they mostly from the C++ community, or are they Python folks looking to migrate to sort of a faster runtime, or what's the drive?
So there is I would say the two main drives are pure C++ people, like people who want to do ND array processing in C++ and are lacking these sort of features for the language. And they are mostly in data science and computer graphics. It's pretty even between academia and industry. Then the second crowd is the people who are building native extensions for the Python programming language. The R and Julia bindings are not quite as successful as the Python bindings, but they are pretty much equivalent in terms of features. There is another notable use case that I really wanted to mention, which is the R-Array package. So by Davis Vaughan, who works at RStudio. And so R-Array is a new array library for R built upon extensor that brings NumPy style broadcasting and universal functions to R. And also there is another use case that we are working on, which is the Pytran transpiler. So Pytran is a transpiler that transpiles Python to C++ that actually works and which is NumPy aware. And so Python already makes use of XMD for the SMD acceleration, and we are now working on using extensor as a NumPy backend in Python.
That's awesome. Any WebAssembly with that as well?
So there have been people like who tried and like made like demo level things, but nothing.
Still a little early times.
Yeah.
Okay, so you and I over the years have worked together on Jupyter and have talked about diversity and inclusion. And just curious what these projects are doing in terms of diversity and inclusion efforts.
So we don't have like a formal thing that we do about diversity of inclusion. We strive to be as welcoming and inclusive to new contributors as possible. We give positive feedback to anyone who comes to the library and opens an issue or like reports a bug. At the moment, I would say that Extensor is still very much led by Quansight, and it was like essentially me, Johan, and Wolf working together on it. But now that the number of stakeholders are increasing, we plan on moving towards an open governance model, move it out of the Quansight GitHub organization. And there are some people who rely a lot on Extensor, and they probably will want to have a say in like direction for the future. Also, we put a lot of effort into the interactive C++ story that I'm going to talk about later, and that lowers the bars to beginners and students who want to learn C++, and I think that's important to bring new people on board.
Absolutely. It sounds like you're making a wonderful foundation for the project going forward, so congrats to you.
Thanks.
Yeah, that's excellent. And I think we now get to move on to the really exciting demo time. You have some just amazing demos lined up for us here, so hopefully we'll be able to get to see them all. So Brandon will be copying them into the chat here for folks to follow along, or you can follow along at home. But if you want to share your screen, Savan, and dive into the first one, that would be amazing.
Okay, so I'm going to run a lot of these demos into the Jupyter. And so can you already see my screen, Anthony?
Yep, yeah, we can see it.
So this is Jupyter Lab, and the splash page of Jupyter Lab, you see that there is already a Python kernel available, and there is a bunch of other things that don't look usual. And one of them is a C++ logo. So I'm just going to demo how C++ in the Jupyter Notebook looks like, what it looks like. So this is the Xus Cling project. It's a Jupyter kernel for C++ based on the Cling C++ interpreter and a library called Xus that is also developed at Quansight, which is a native implementation of the Jupyter protocol, the C++ implementation of the Jupyter protocol. So Xus is not a kernel itself. It is a tool to make kernels, and we've made several kernels with this. And including the C++ kernel. So let's write some C++ code. So if I do hash include iostream and do std cout and print some string, it gets printed right away. And this may look like really simple, but we've got to appreciate that this code is being compiled. This is C++ here. So, and I'm making an interactive usage of the programming language. So I have like the classical output, text output, error messages. It's catching exceptions as well. If I omit the last semicolon of the last line of a cell, which is not valid C++ normally, actually the value of that cell is going to be returned. Just like in Python. I can interpret the C++ programming language, so use classes, make use of polymorphism, templates.
Nice.
Yeah, this is really impressive. Like, so where are all these things going into a common like context, or how is this all working?
Yes, this is incrementally compiling and adding new symbols to the Clang state, I would say.
I see.
So this is all in the same context. Here I am reusing some class that I defined just earlier. It's not a different program per se. It's really like an interpreter sort of workflow.
Interesting.
We support documentation. So if I do question mark std vector, it's going to load the documentation.
Oh my God. That's so cool.
And it is not a gimmick. So if you do this for extensor, for example, it's going to look it up online for the read the docs documentation for extensor.
Wow.
So we provide an APIs and means to do this for user-defined types so that you can easily use this as a tool for teaching C++, for example. So the C++ notebook supports rich display. So for example, here I am creating an image type. All it does is loading a buffer from an image file. And I just have to override a certain function called MIME-bundle-wrapper, which is going to be picked up by the system through argument-dependent lookup, which is a feature of the C++ programming language. And now if I create an instance of an image and display it without the semicolon, I'm going to see the image instead. So now C++ can make use of the rich display capabilities of Jupyter. This works with any sort of MIME type. This one is an HTML MIME type that has an audio tag. I'm not going to play the audio, but
we believe you.
You can see the audio tag, or we can update existing things that were displayed. For example, here I have a blue rectangle, and if I run the next cell, changing the color of that rectangle, it gets updated to red. I can also clear the output. Another interesting feature of the classical Python kernel are magics. And magics are, I would say, additions to the language that allow to perform some things that are orthogonally to the code that you run. So here I'm just doing like a timeit to measure the average time required to run a given line.
That's really impressive. That is so difficult to do in normal C++.
Yeah, that's fantastic.
So we're working on making the magics a extensible thing, just like in IPython.
Right.
Yeah. So I'm going to do a lot of the demos of extensor using that. And so I said earlier that extensor is essentially NumPy for C++. And what I want to show here is that what you get with extensor and Jupyter and the C++ kernel is an experience that's very similar to that of NumPy with a Python kernel. So I'm just going to make a few includes. Essentially a 2D array and another array, and here add a row of one array to another array and see like the expected result. This uses the rich display features of Jupyter to actually make a HTML view of these tensors. And when you hover on any value, you see the corresponding coordinates.
That's so cool.
So for example, you can initialize a 1D array, reshape it in place, display it. You can do universal functions like power. Here I'm like taking an outer power of two 1D arrays to generate a matrix. And you can generate random arrays like with a random module. And for those who are really familiar with NumPy, they will actually see that these APIs really look like those of NumPy's. Instead, you would do np.random.random, right? We have a few other things inside, such as like the type that you want returned, right?
Mm-hmm.
And here I am doing some fancy indexing to actually return the array of values where it's greater than 0.2, right?
Mm-hmm.
And here we summarize the output, not displaying all the rows because it's really big.
So just a quick question here, since you're templating on the type, what sort of range of types does this actually work on? Like, would it work for a custom class that you wrote, and would it work for things like C++ standard strings and
anything? Literally anything.
Yeah, and so
if you write a new type that, for example, has arithmetic operators, you will be able to use arithmetic operators on extensor of these types.
Amazing.
And now we also have means in extensor. If you have a structure that has a few methods that you want to use as an element type, we have a means to parameterize the base tensor class so that these methods also can work with the tensor and return expressions that return tensors of these of the return values.
I see.
So for example, we can get the real or imaginary part of a tensor of complex values as tensors.
Gotcha.
Yeah. Or like same for missing values, whether it's missing or not, like optional values. So as I said, we have very similar APIs to those of NumPy, like linspace, initializers like ones, arange, and whatnot. More complex features such as broadcast. You can also use standard algorithms on extensor. Like here, I'm using standard accumulate on a random array. One thing that I really wanted to sort of emphasize here, which I haven't told yet, is that extensor looks like NumPy and gives you the feel that you're actually operating on arrays, but most of the time you're actually not operating on arrays. You're operating on unevaluated expressions. So, for example, when I do linspace with extensor, it does not return an array; it returns an unevaluated expression. And every time you access an element, the element of linspace is going to be computed. Things are only evaluated when you access them or when you assign them to a container, right? So in that case here, random is not, I'm assigning to an array, so it's evaluated, but I could totally have assigned this to an auto variable, and every time I accumulate, I recompute the random numbers.
Oh, so, interesting. Yeah.
So when you do A plus B times C, the result value of that is not an evaluated array, but it has all of the methods, begin and the iterators to operate or traverse the values and accessors, but it's not an array. It can be assigned to an array, or it can be accessed, and every time you access one element, just only that element is going to be computed. And running all of the loops.
Yeah. Is there a way to force the evaluation of an expression if you want to without accessing, or the evaluation of an array? Or
you can assign it to an array, and that's going to become an array.
Okay, yeah.
And so you can force it. There is also an xteval function that is going to return the best array type for the computed value. So that is something that I really wanted to emphasize here, in that it looks like NumPy, but things that you get are not arrays. And that actually makes it very efficient in that we prevent the creation of temporary values. When you do A plus B plus C, for example, we don't assign or allocate B plus C. We just unroll all of the loops and perform and like compute the expression element by element only.
Right. Yeah. it's similar in that way to things that we've seen on this program before, such as PyTorch and you know, and I think NumPy and
But one thing that Extensor is also going to do is that it's going to operate in batches when it can. For example, if you add 3 vectors that are well aligned and everything, when you do A plus B plus C, it's going to use SIMD operations to add the elements in 4x4, 8x8, depending on the size of the elements and the number and the available instructions on your chip. So, for example, including complex operations, so it could be A times C plus D multiplied by some exponential that we compute using SIMD as well. So things are parallelized, and the generated, I would say, assembly is completely equivalent to unrunning all of the loops and making explicit use of the SIMD intrinsics for your chip. So the results are really fast.
That's pretty neat. Does that just happen when you're using this interpreter, like when you're using the Kling interpreter, or does that happen when you compile it into a library as well?
In both cases.
Okay.
Yeah. So another quick demo of Extensor Blast. So Extensor Blast is the extensor implementation of NP-linalg, and I'm just showing that you can do some Blast operations. One thing that is interesting here in the case of Extensor Blast is that we actually load the Blast binary on the fly as we include the header. So we don't need to actually load the DLL yourself. It's included into the headers for Extensor Blast. So it's really just like a script. So since I showed that, I just wanted to show you, can you see this? This is a cheat sheet for NumPy to Extensor. So basically Python 3 and NumPy to C++ 14 and Extensor. So we show like some equivalence between, so the left-hand side being Python and the right-hand side being C++. So for an NP array, for example, you can initialize various expression types on the Python side and the C++ side, meaning xarray, which is very much the equivalent to NP array, or extensor, which has a static number of dimensions. And when you know how many dimensions you are going to have, extensor tends to be faster because more things can be inferred by the compiler. You can reshape things in place. You can cast things. We have initializers like linspace, logspace, arange, I, zeros, and all of these return unevaluated arrays, or even complex ones like meshgrid. You can do broadcasting, including the new axis features and ranges. We don't have the nice slicing APIs that Python has, but in terms of features, it's completely equivalent. You can vectorize functions, filter, do some fancy indexing. We have the random module, concatenation, rearranging elements. And we offer multiple ways to also operate on iterate and traverse arrays. So for example, you can traverse arrays with a row major order or column major order. You can also prescribe a broadcasting shape if you want to see a tensor as a tensor of a higher dimension or a different shape.
Yeah.
Wow, that's a great cheat sheet too.
Yeah. Logical indices, comparisons, minimum, maximum, complex numbers, reducers like sums, etc., with very much the same API as NumPy everywhere we can. Loading NPY files, CSV files, image files, mathematical functions that are all SIMD accelerated, linear algebra, and whatnot. So API coverage from Extensor of NumPy is one of the main goals of the project.
Yeah, that's amazing.
Fantastic.
Do you have any other demos you want to share here?
Yeah. So one is Extensor IO. So Extensor IO is one of these binding library for loading files. And in this example, I'm loading some image file and displaying it in line. So here it's a lightsaber. And I'm using Extensor IO and Extensor to actually create a small GUI where I have this slider, which is a Jupyter widget. And anytime I move the slider, there is some operation done on the image that gets updated in the notebook. So it's very easy for a user of C++ or beginner who would like to get some visual outcome of his code to actually get these sort of things and build these sort of applications without having to do any Qt programming or web development themselves. Or you can do the same with audio files and whatnot. Extensor.io can also load videos, NPY, NPZ, MATLAB files, lots of them. So I showed like a quick example of a Jupyter widget. I just wanted to mention real quick that we actually have C++ backends to most of the popular Jupyter widget libraries. One example is xleaflet, which is a mapping library that allows you to create interactive maps in the Jupyter notebook, upon which you can draw, you can add data interactively. And in this example, I'm just loading a JSON file and adding it to the map. And these are like ISO lines. And normally, it's like these sort of things are pretty hard to do in Extensor. So in C++, talking to a web frontend like this and getting a leaflet map to update. So interacting in this environment with the Extensor and XStack makes it really accessible, in my opinion.
Yeah.
It's fantastic.
It's incredibly impressive.
So you asked earlier whether it's possible to operate on items that have are custom items. And so here I recall what Extensor is, like ND arrays for C++. And I just wanted to give a shout out to SimEngine. So SimEngine is a C++ library for symbolic computing that was created by the authors of SymPy, and it's one of the possible backends for SymPy. And here I'm showing that we can do some symbolic programming natively in C++ in the Jupyter Notebook, and expressions that are returned by SymPy are actually by SimEngine are actually rendered with LaTeX in the Jupyter Notebook.
Beautiful.
You can combine Extensor and SimEngine. So, for example, here I'm adding a symbol which is Z to a linspace, right? Here I am like doing an outer multiplication of e plus y times itself, right? And like computing the sum, and everything is done like SimEngine takes care of simplifying the expression and like returning something meaningful.
Wow.
So you can, really, and all of this is done lazily, obviously, because Extensor is just an expression system. So things are only computed when I compute the sum here, including all of the SimEngine magics.
Wow.
So the last demo is xframe.
This is the xframe. Yes.
Xframe.
Yeah. Perfect.
Well, it's like the title of the webinar.
Right? Yeah, we had to get to it at some point. That's right.
So xframe, too long didn't read. It's a data frame for C++ based on extensor and XTR. We follow a data model that is very close to that of Xarray, meaning the netcdf data model. So this is still early stage, and probably not exactly what the API is going to look like when we release 1.0. But still, I wanted to share it with you and see so that you can see the sort of things you can do. So as I said earlier, Xarray has a very similar API to that of, xframe has a very similar API to that of Xarray, in that data frames are actually collections of variables, and variables are tensors with named dimensions and indices in all directions, right? So just to illustrate what I'm saying, I'm just creating some 2D tensor here with some missing values.
Right.
And some axes for, let's say, this is the temperature in London, Paris, and Brussels at different dates, right? Now I have a variable here, which corresponds to date 2018-0104 and city London. So when I hover on one part of this variable type, I will see both the data and the coordinates for this data. So there are multiple kinds of indexing. So for example, I can directly index by positional lookup. I can also do a dimension lookup by label.
Mm-hmm.
Yep.
I can also do dimension lookup by name and index lookup by integer. And then dimension lookup by name and index lookup by label. So all of the possibilities are actually provided for a variable, just like in xarray.
Fantastic job.
So, and then you can do broadcasting and math on the top of it. So you can add the water vapor pressure is some formula corresponding to the relative humidity, dry temperature. And just like extensor, xframe is actually not really a data frame. It's a data frame expression system that is lazily evaluated. So things are computed on the fly, and only when you access them or when you assign them to a data frame.
Yeah, I'm not sure I've seen another extensor kind of lazily, or an xframe-like thing that exists. That's
so
in terms of
you can also do like higher dimensional variables. Yeah, exactly. It's the thing is, we really, just like we were following NumPy for the API of extensor, here we are really trying to be as close as possible to xarray. And we even have the same sort of cheat sheet from xarray to xframe. Python 3 xarray, C++ 14 xframe, where you have containers, indexing, logical operations, comparison, mathematical functions, and whatnot.
Right.
And just like we try to have the highest coverage as possible of NumPy with extensor, we are trying to get the same sort of coverage with xarray.
Wow, that is so impressive. I mean, my jaw's on the floor here. If C++ was this easy 20 years ago, who knows what I would have been coding in.
Yeah.
Yeah.
So we have the same sort of selection APIs for getting views with a dimension lookup by name or value and index lookup by label or integer.
Right.
And you can keep and drop label, make fancy indexing, reindexing views, or pretty much anything xarray can do.
I mean, I feel like you could just keep demoing forever, but we also have a roadmap discussion to get to and a lot of questions. So why don't we move on to our roadmap right now? So again, this is a place where the whole X ecosystem or extensor ecosystem these are places where they're looking for contributions or funding and sort of the directions that the project is going in or the projects are going in and sort of and all the next steps. So your roadmap must be huge, but what's on it?
There is a lot, but we need help and funding, obviously.
Yeah.
So there are various degrees of maturity in these projects. I would say that XCMD is essentially done. It's a simple library that does its job. And all we can add to it is new implementations of like special functions or new instruction sets, but it's not going to move too much from a user perspective. Extensor is not as close to completion as XCMD, I would say, but it's getting mature and more projects are relying on it. And xframe is still very early stage. So our focus for the next year is very much going to be on xframe and getting it to a point where we can announce officially a C++ data frame.
And so what sort of help do you feel like you need to make that a reality in the next year?
I think we need more people. We need help from people who have experience building data frames. So we are talking actually a lot with people who have, we've been talking to Wes, obviously, and to people who are building C++ data frames at CERN as well. And so we're really trying to do it right and get their input as much as possible. We have already found pitfalls that they knew of, and so it's been I would say useful to talk to these people.
Of course.
And so also we are a small team. So Quansight is just 5 people, a handful of people, and mostly also working a lot on Jupyter and other pieces of the ecosystem. And so if you want things to come earlier, we need more money to get more people on the project. There is a more like high-level item on the roadmap for us, which is to figure out a sort of more open governance model. We have seen that some people in academia were worried that this project was driven by a company, even though we are very invested in the open source ecosystem, and we also play, roles as volunteers and community organizers. They will probably be more comfortable with Extensor if it was not a Quanstack GitHub organization. So we need to figure that out.
Right.
Yeah. Well, you're in good hands with that, I think, between your work on NumFocus and Jupyter Steering Council. And you've got great stuff here, and a lot of folks on your team that come from academia.
Yeah, most of them, yeah. NumFocus is probably a good home for Extensor. I didn't want to submit Extensor as a sponsored project too early either. I think there is a sort of need for things to be developed by a reduced team in the beginning so that we set the scope and then we push it out in the open.
Yeah, that certainly makes sense. Too many cooks can spoil the soup. So are there particular items that, folks could jump in on and either fund or get give code contributions to get off the ground that you just know that you might not have time to do or not have time to do in the near future?
Yes, there are items for which we would really like to see happening that are not funded by clients who are interested in Extensor at the moment. For example, Extensor Julia has not found an audience compared to Extensor Python or Extensor R. And I actually think that there are interesting opportunities to make a much better use of the Julia type system in the Extensor Julia bindings than what we can do with the two other programming language. And so I'd be really interested in going crazy with the Julia type system in these bindings. So that's an area where we think we may need help. The Python migration to Extensor for us would be like the ultimate unit test. Python has a huge gallery of NumPy to C++ translation examples that are tested, and the thing is, we're going to catch a lot of performance bugs and bugs in Extensor if we manage to move Python to Extensor, but we're not funded for that either.
Right. So so who works on Python normally, and who's able to, who's interested on their side, and just, I guess, what would it take for them, and maybe if you could just give a very brief introduction, a one sentence introduction to what Python is for those folks who might not know.
So Python is a compiler a transpiler from Python to C++ that produces really fast code. It's actually really hard to beat, and we actually found a lot of performance bugs in Extensor, but just trying out the equivalent code of NumPy and transpiling it with Python.
Oh, funny.
So it can the C++ that it produces can be used as a program that you use from a C++ library, or it can also directly be exposed to Python automatically, and you can call it from Python. So with a very simple magic in the Jupyter Notebook, you can compile a cell to Python. It's not going to compile all of Python, so it's pretty much a subset of Python corresponding to what you would do in a numerical kernel, I would say. It's mostly developed by Serge Guelton, who is like the main author, and there are a couple of other significant contributors. I don't have their names on the top of my head right now.
No, that's fine. I think we're going to end the roadmap discussion there, just in the interest of time, because we have so many questions. So we're going to get to those now. But just a last reminder: if you're interested in this or any other aspects of the Xtensor ecosystem and roadmap, please contact Sylvain to either fund Xtensor or to jump in with contributions, as I'm sure he would love them. So with that being said, let's go ahead and get on to our Q&A section. So David from Twitter asks, as far as I know, there's no NumPy-like Python library that uses xtensor as the compute backend. That would be possible with xtensor Python, but would it still offer the benefits of lazy evaluation and optimizations across functions?
So Extensor Python is mostly meant for people who want to create Python extensions that consume NumPy arrays and operate on them in place. So it is not creating a new Python type. It just lets you see NumPy arrays as extensor expressions in your C++. So we didn't try to make a competition or like an equivalent to NumPy, like QPy was doing.
Right.
We leave NumPy where it is, but if you want to create a fast C++ extension that operates on NumPy arrays, you can with Extensor Python. And actually, using Extensor Julia and Extensor R, you can expose the same C++ package to Julia and R and have it operate on the native data types of these programming languages. Now, there is a very interesting project actually coming from Quansight called UArray, and I think this would be a great use case for UArray to create an extensor-backed NumPy clone. This would probably also be a very interesting test case, I would say, for Extensor, because we probably catch all the cases where we don't behave like NumPy, just like Python.
Yeah.
And finally, in terms of lazy evaluation, I don't think that we could benefit from all of the advantage of Extensor, meaning the evaluations that are compiled by a C++ compiler. But for those that you use a lot, for example, you could totally compile them and add them as new UArray arrays, I guess.
Yeah, that's a callback if I've ever heard one. You can go check out our UArray episode, which is the last episode. So.
That's awesome. Great! I didn't know that.
Yeah.
Okay.
Yeah. Okay, cool. Should we move on to the next question? Is from Kenneth Hanley. And hey, Sylvan, with Extensor and xframe offering great alternatives for NumPy and Pandas, are there any long-term plans for a Sci-Fi alternative?
There are alternatives plans for numerical libraries making use of Extensor and xframe, but not really a systematic, Sci-Fi counterpart like we were doing with the APIs of NumPy that we're trying to cover. So I assume that there will be a growing ecosystem of libraries using Extensor as a base array type. But yeah,
that makes sense.
Excellent, thanks. So Travis asks, how are universal functions and generalized universal functions managed within Extensor?
So Extensor does not have a notion of generalized universal function. It only has a notion of universal function. And all actually operations like the plus operator are implemented in that way. Within Extensor, the universal functions are called X functions, and they are really baked into the expression system. Any expression is by default going to be a combination of universal functions. Broadcasting is, since it's compiled in C++, I would say that we try to take advantage as much as possible of what is known at compile time about the expressions. For example, some of them may have completely static dimensions or a static number of dimensions. Or we may know that by construction, some expression is contiguous in memory and has a certain layout. And we are going to optimize and try to detect as much as possible of these things to create or produce efficient binary code.
Cool. We have another question from Travis as well. What would it take to have a NumPy module that translates to Extensor?
Pytran. I think that's actually precisely what it does. Yeah.
Fair enough. Good answer.
Yeah. So Anna asks, is there some analogy for, or some analog rather, for an apply function that allows passing a lambda function into an extensor?
So if I understand the question well, if it's apply a lambda to every element of an array, you can pass a lambda to an X function and create I would say, a vectorized functor from a lambda very easily. It's just one liner called xt.vectorize. You also have means in extensor to create lambdas, to create functors that would be SIMD vectorized if you know how to vectorize it yourself.
Awesome. Another question from Michael. Do you have a demonstration of extensors, Python bindings in a Jupyter notebook?
Yes, but I don't have it handy right now. But if you want to see it, you can check out our JupyterCon talk on Zeus. I can add the link later on. And in this, we have a notebook in which we create bindings for Julia, Python, and R on the fly in a Jupyter notebook.
Fantastic.
Hamir asks, how close are the xtensor Python bindings to NumPy?
Well, extensor Python bindings are a means to operate a NumPy array from the C++ side. And I would say that then you are in extensor world and the API really looks a lot like NumPy. The extensor Python bindings don't create any new Python type at the moment.
Gotcha.
That sound stuff. Okay, so from David, automatic alignment is supported in xframe, which is great. But when working with floating point numbers, allowing almost aligned coordinates becomes necessary. As far as I know, tolerance is not implemented in xframe yet. Any plan to do it?
Well, we didn't have any plan to do it, but if that's a feature request, it's interesting. I was not aware of this feature. One small note here is that the alignment, so the way we align data in xframe, it does not 100% correspond to the semantics of xarray. So this may be done in a slightly different fashion eventually. Meaning that xarray and pandas have means to have multiple values for one value of the index. So I would say that, yeah, xframe coordinates are not an index in the sense of pandas.
Yeah, understood. So Travis asks our last question here. Does xtensor have any GPU integration?
Not yet. That's a big roadmap item for us. We are looking into single source approaches here. So essentially CUDA or Cycle. Actually, we are already talking to some chip manufacturers about getting some of that work funded, but it's not a certain thing yet.
Right. Yeah. Why stop there? There's FPGAs and the whole other ecosystem out there too.
Oh
yeah. So at this point, we are now ready for our world famous rant section, where we each get 15 seconds to rant about whatever topic we so choose. Sylvain, it is your soapbox.
Okay, I think there is one thing that is absolutely not tolerable. It's the delete for GitHub button. I have a compulsive need to click on these buttons, and I have already deleted forks where I had lots of branches and everything. So please remove that button.
I wholeheartedly agree with that rant. And my rant is just remembering keyboard shortcuts across all the many different things that we use is kind of a challenge, at least for me. So,
for my rant today, I would just like to remind people that it is primary season in some parts of the US, including my home of Philadelphia. So please remember to go out and vote on Tuesday or whenever your elections are. That's all the time that we have for today. Thank you so much for watching. Thanks for listening. You can find us on Twitter at Quansight AI. If you're interested in funding open source projects, including xtensor and xframe and the whole X ecosystem, you can find all of the project roadmaps at quansight.com/projects. Sylvain, where can people find you and xtensor?
So you can find me on Twitter and GitHub under the Sylvain Corlet handle. And Extensor and all of the companion projects are available on GitHub in the Quantstack organization.
Excellent. And thank you, and join us again next episode for a studious discussion on scikit-learn.